So again, you can just kind of follow along with my handout. All right, so let's remember a few things about light from Chem 1. Light travels in waves, like I've shown in the picture on the bottom of the slide here. Sorry that yours is in black and white, but mine's in color. Frequency is how often the waves occur. So a long wavelength has a low frequency. We're actually covering this exact same stuff in Chem 1 right now. Now, amplitude is usually referring to the height of the wave. We don't worry about that too much in Chem 1. I think physics might worry a little bit more about amplitude than we do in Chem 1 or even in AP chemistry. But those are common terms when describing it. Speed of light, sometimes it's rounded to the hundredths place, which is, I believe, 2.98 times 10 to the 8th meters per second. Oftentimes we just round it to the ones place and call it 3 times 10 to the 8th meters per second. Again, if it's traveling through a substance, it could travel a little bit slower than that, but that's typically the speed of light. Next class, we do have to remind you about light calculations. So it's either next class or the class period afterwards. So I know next week we are covering that, so we'll go over that number again. Now, a few other things to talk about with light. I had someone in Chem 1, because we're actually talking about light in Chem 1, mention this yesterday, like, oh, in Phys World we were taught this. So, you know, my tie is blue, so that must mean that it's, you know, absorbing all the other colors. And she was confusing how, when we talked about how things give off colors, electrons jump up, fall back down type stuff, with absorption versus transmittance. Because to absorb means, yeah, if this is showing blue right now, that means it absorbs all the other types of light, but it's transmitting or reflecting off the blue. So the idea of absorption versus transmittance is something that we vaguely have to be aware of, but not too much, really. When we work with our spectrophotometers today, we set it to a certain wavelength to ensure that it's, you know, capturing the correct type of light. And that's kind of the key with what that piece of equipment is going to be using. All right, so our spectrophotometer. Again, it doesn't look like it has a lot to it, because if you look at it itself, there is one button on it, right here. And that's basically the same as your tare or zero button on a scale. There's a dial on it, which we'll talk about that in a minute, but then there's a place where you put your solution, and that's it. However, again, first off, it has a very powerful bulb in it. And what a spectrophotometer does, if you look at this picture here, in the middle it says sample cell. You're going to have a solution, and we use this with colored solutions. Light is going to shine through that solution. Now think about it. If it is a darker solution, less light should pass through, right? If it's a lighter solution, more light can pass through. Well, what it's doing with the meter on the far right-hand side here is it's measuring and giving you a value of how much light was able to pass through. What we will be able to do then is use some mathematics with that value in order to determine the concentration of the solution. So typically what we do, like what we're going to start with next class period, is we are going to measure how much light passes through a known concentration. Then we can do a little bit of math, maybe make a graph like a line. And then we're going to put something in that sample cell that's an unknown concentration. Doing a little math, we can figure out what the concentration is. That's basically the lab next time. So you have a light source. The monochromator is just going to adjust what wavelengths are passing through, because there's an optimal wavelength for any type of solution, and that's what we're going to try to figure out today, is what's the best wavelength to do our experiment at next class period. Then you have to have a detector, so what's picking up the amount of light, and then what's actually giving us that reading. So again, there's not a lot of bells and whistles on it, but really the light bulb itself is fairly expensive. And if we have issues with that, it's no longer useful to us. This is another reason why I printed off these slides, because, oh my goodness. Let's have you guys write this down. All right, so this just explains kind of what I was talking about, is that you have a lamp that's going to shine light through hitting material, and then based upon how much it's hitting through, it can then give you an idea of how concentrated your solution is. Again, I'm not going to read all that right now, but you have all that text with you if you really wanted to do that. here's what we're going to be doing. So this is on the back side of your sheet. Is we are going to be doing some math with this. And what we're going to do is look at how much light is absorbed by a solution. And by doing that, we can do some math to figure out what's the concentration. And like I said before, my second bullet point, if there's more light absorbed, it must be a higher concentration, because the light can't pass through thicker stuff. All right, so today's goal is we're going to determine what is the best wavelength to do our experiment at. We're going to create a graph similar to this on your lab packet a little bit, where we're going to be measuring the absorbance at different wavelengths. And what we want to do is we want to find which wavelength can we get the best results at. Because some wavelengths aren't going to be picked up by the blue solution very well. And if that's the case, it's not going to help us out when we vary concentration, because it's just going to give us zero values no matter what we use. So we're looking for a peak today. I mean, even something as simple as this graph I've seen on AP questions before. Because if you have never worked with this piece of equipment or done spectrophotometry, you have no idea what this graph is. But if you have, it's a pretty straightforward, simple graph, where it looks like to me around 580 nanometers is the optimal wavelength that I would want to do that experiment at. It's just that without that experience, you're unsure of that. So again, the best absorbance is what we're going to be doing. So today's goal is to figure that out. Next class, what we are going to do is what's called a Beer's Law plot. And the sheet that you picked up on the way in, that's the topics, the Beer-Lambert law, again, this is something that AP expects us to know about. So there's two ways we can do this type of work with a spectrophotometer. Next class, what we're going to use is our graphic analysis on our Chromebooks. So we can do Google Sheets, we can set up our data, we can create a graph like this. And if you create a line graph and then you measure the absorbance of an unknown, you can figure out what the molarity is. Now there's another way we can do that besides that, and this is mentioned on your goal sheet of there's an equation that is given to you on the equation sheet for AP, which is big A equals ABC, where big A is the absorbance, that's the value that the spectrophotometer reads. Little a is called molar absorptivity. It's a constant value that you kind of plug into the equation to make it work. B, sorry, that should be lowercase b, I think it just auto-corrected on me, is the path length. So how much does the light have to pass through? If you had a thicker tube versus a smaller tube, it makes a difference. Our path length for our spectrophotometers is usually 1.1 centimeters. And then lowercase c, it should be, is the concentration. Now, what I can tell you is last year, because of all the snow days, there was a lab that we were going to use this over and over again for. I had to cut it because we had too many snow days. We had to figure out a way to make sure we had enough time to practice at the end of the year. And don't you know, last year was the first time in a while that they actually had this equation that people had to solve on an AP exam. So, we're going to try to fix that a little bit. I adjusted your lab this year to make sure this was on one of the post-lab AP type questions, just so you get some experience with it. Again, based upon what we're already seeing now, I don't know if we're going to even have school for the month of February because there's going to be so much snow out there, but who knows? Maybe it'll be the exact opposite, that February will be completely clear because we're just going to get the snow out of the way early on. Either way, I want to get practice with this a little bit when we can. All right. My last slide is more talking about the spectrophotometer. Again, even now, when I look at that window, it says warming up. Now, it says you can press the button to skip, but that bulb needs time to kind of get warmed up and get to a good position. So whenever we do spectrophotometry, we need to get these things started right away because it determines when we do our work. Now, next class, we're going to have to do some dilutions. Remember M1V1 equals M2V2? So because of that, while we're doing our dilutions, we can probably let the machine warm up, and by the time we're done diluting, it'll be warmed up, we'll be ready to go. But in general, we can't unplug it at any point or turn it off, because then we got to wait again. So we turn it on, we let it warm up, and then we do our work. The zero button. Remember how you put like a weighing boat on a scale, then you hit the zero button, then you put stuff in it? Light can be absorbed by any matter. Now granted, if it's a colored solution, like we're working with blue dye number 1 these next 2 days, that will absorb more light. But our little test tubes, which by the way, our little test tubes are called a cuvette, they can absorb light because they have glass. Water absorbs some light. After all, our solution is dissolved in water. So we have to zero with distilled water in order to do our experiment. Just like we have to zero with a weighing code. Because if we don't, now it's not just the blue dye that we're measuring. It's the blue dye, it's the glass, it's the water part. So we have to make sure to do that. This thing is so precise that you don't want fingerprints on this. Because fingerprints, oil, can absorb light. So whenever you're doing spectrophotometry, you make sure to have a paper towel or something nearby to wipe with. Now you see that there's this little white mark here? The light's passing through below this. So if you're holding it at the top, you'll be perfectly fine. But again, usually what people will do is they'll fill it up, they'll wipe it off, and then they'll set it in the machine. And it's a snug fit. So you gotta push that in. Close the lid. You gotta close the lid or else outside light is going in there as well. Again, I want that lid closed whenever possible. I don't want it just left open because I'm gonna fill up something too. I had 1 year, and it was at this lab bench, that someone, I don't know, just grabbing too hard, he broke the glass. And then when that happens, now we have to try to get glass out of this. So I had to take it completely apart. And this is not the same machine anymore. Because once I took it apart, I don't know what happened. I was careful, but it's back there. It's our backup. Because it was not giving us good data at times. So you got to be careful when you take it in and you pull it out. Heck, there was one time that a group left a solution in here at the end of the day, and then we put everything away. Ooh, we should not do that, because what happens if we spill that into this really expensive piece of machinery? Not good. So again, we got to take care with this, because it is a very precise thing. Now, if I had water in here to zero it, and I dump out my water, and then I put in my blue solution, if there was a couple of drops of water still in here prior to adding my blue solution, I just watered down my blue solution. Does that make sense? Little remnant in here, now you add. No longer then is the molarity in here what I think it is. If you get yourself in that issue, once again, this really precise equipment is going to pick up on it. So it's going to say, here's the absorbance, but you're going to think it's for the molarity written on the bottle, but actually it's less than that now. It's kind of one of those sources of error. When you turn to the lab to talk about sources of error. So what we suggest doing, which seems a little wasteful at times, and I get it, is you rinse this with what you're going to put into it. So when you get started at the lab today, it looks like I have to put some plastic pipettes out for you. But you're going to squirt some in here, rinse it around, then dump it out, then fill it up to about that white mark. Now it's ready to go. But if you don't do it that way, you're going to throw off your results. What we're going to be doing today is we're going to test one sample at multiple wavelengths in order to make sure that we have the appropriate wavelength for next class period. Next class period, then, we're going to be testing multiple samples. Make sure you don't mix up which concentration is which. Because once again, is this the 0.05? Is this the 2? If you do that sort of error, that is going to make your graph look ridiculous. That's not going to help you out at all. So my hope is this first little intro notes was meant to give you a little background on the piece of equipment you're going to use. If you could have out the analysis of food dyes and beverages lab,